Could we begin with the first slide? I propose to discuss what is known about the universe around us on very large scales. A good place to start is with this image of our planet Earth. Perhaps some of you remember, now how do I change slides? I should have a slide advancer. Maybe some of you remember the excitement of images of the full face of the Earth when first released. They certainly inspired a small subgroup of people to undergo what we now term sustainable living. I hope we will soon see one publication devoted to this exercise from those early days, the Whole Earth Catalog. Perhaps you know it, perhaps you've thumbed through it. Fascinating stuff, but almost all of it hand tools. They were onto something, of course. This is the theme of this conference. It might be good. Here we have the Whole Earth Catalog. Stuart Brand, in some circles, dismissed as a dropout. But in fact, these people were certainly onto something. Let's see if I go forward. Well, I go backward? Yeah. I want to pause for a minute to ask you to admire these clouds. Once one sees the pattern produced by the sun heating the earth unevenly heating the atmosphere moving, the rotation of the earth causing the atmosphere to develop these wonderful patterns. Here is the largest planet in our solar system. It is almost entirely atmosphere, mostly hydrogen and helium, trace elements of methane, ammonia, water vapor. Here, convection is driven by heat coming from the center. This planet is still cooling off from formation. The convection up with rotation produces these delightful patterns. Here is a satellite of Jupiter, one of the Galilean moons. Here we see a very different pattern. This is thought is a pattern on a sheet of ice covering the planet, floating on a sea of salty water. Human nature being what it is, it's no surprise that there is a strong move to land a spacecraft on the surface of this moon, drill a hole, and sample what's in that salty water. We are, of course, moving around a star, the sun. Here is a map of the nearby stars. We are in the center. The size of each symbol is a measure of the physical size of the star. The most massive of these stars is Sirius A, the blue star. High mass means far more rapid burning of nuclear fuel, producing a hotter surface, much greater luminosity, shorter lifetime. That blue star has a companion, a white dwarf. It was even more massive, we infer, burned its nuclear fuel even more rapidly, and collapsed to a white dwarf. You see that there are several stars larger than the sun, and a whole lot more that are much less massive than the sun. Perhaps you can see down slightly to the left of center and toward the bottom, two moderately large stars, and near them a star with a mass about 0.018 times the mass of the sun. It is just heavy enough to ignite thermonuclear burning of hydrogen. It has achieved some fame because it has been found that there is a planet moving around that star at a distance such that it is neither so hot as to drive off all water or so far away from the star as to allow the water to be frozen solid. You can imagine how interested people would be in visiting it. Here I advertise that Professor Lisa Kettenaker, close approximation, will tell us about research by her and colleagues that shows us that there are at least as many planets around stars as there are stars. There's got to be a lot more planets in this general area, and as you can imagine, people are already talking about how they might be able to send drones to sample just a little bit what's on those planets. Here is a larger scale distribution. Well, how do I get back? Left. Nope. It seems to want to go forward in either direction. Here we are. Here is a larger scale view of the distribution of stars in our neighborhood. Our galaxy is like a pancake supported by rotation. We are in the pancake. When we look along directions through the pancake, we see the light from many stars. You see dark bands. That's not absence of stars, but rather presence of interstellar dust that is obscuring the starlight. Here is an image of a nearby another nearby galaxy, one that is rather similar to our own. You see blue patches here and there. That is where interstellar dust and gas have collapsed, formed new generations of stars. In a new generation, the short-lived, most massive stars are by far the most luminous. They're the hottest, the bluest, hence the blue light. You see also here and there red patches where massive stars have emitted enough ionizing radiation to produce a plasma. The plasma is shining by recombination radiation because most of the plasma is protons, nuclei of hydrogen. The most prominent recombination line is the 6,000 angstrom line of hydrogen, gives you these blue patches, or these red patches. You see in the center yellow haze. In reality, that yellow haze continues through the whole galaxy. It is the light of several thousand million stars, similar to the sun. It is a good bet, as we have seen from our neighborhood, that there are, therefore, in this galaxy, several thousand million planets on which we can be sure all kinds of fascinating things are happening that we can be very sure we, as a human race, will never see. This being some 8 megaparsecs, 5 megaparsecs away, some 15 million light years away. Things are happening that we will never know. Here is a map of the distribution of the nearest galaxies. The coordinates are chosen to put a plane of galaxies in the equator. You are seeing two views, one looking straight on at this system, the other, the view you would see at 90 degrees. You notice some 24 red dots. These are galaxies as massive as our own. There are none much more massive than our own in this neighborhood. Down below, you see examples of some of these galaxies. You also notice in the upper left, in the left-hand panel map, that there is one little galaxy all by itself in a big empty region. An image of it is shown at the far left. It's a negative, so you can see more clearly the presence of a knot of stars in the center. Surrounding it, you see the contours of atomic hydrogen. There's a vast cloud of atomic hydrogen around that little knot of stars. There is evidence that stars occasionally form in this small knot, but it's a rarity. Here is the distribution on still larger scales. You see at the very center a rich cluster of galaxies. It is, in effect, a galaxy of galaxies. You see also something new, namely, as we have gone to this scale, we have stopped seeing anything new. The left-hand side looks a lot like the right-hand side. This is our homogeneous universe, clumpy on small scales, but very smooth on large scales. That smoothness is what allows us to make a theory of the universe rather than a theory of one or another part of the universe. Homogeneity means that we can think about a global picture for how the universe is evolving. In particular, we know that this distribution of galaxies is moving apart, it's expanding. The general notion of this expanding universe is well worth noting. It goes back, of course, to Einstein and his theory of general relativity, a new theory of gravity physics. You see in the upper left, with Einstein, the Leiden astronomer Willem de Sitter, who was a very stern critic of Einstein's early attempts to arrive at a theory of the universe. Einstein took it, I think, as a given. The universe is forever. I think Hermann Weyl was one of the first to point out that need not be so. But so far as I know, he didn't have a full theory of the expanding universe. Alexander Friedman did, but the misfortune to be born too soon to know about the astronomical evidence for an expansion. Georges Lemaitre, shown on the bottom right, had just the right talents needed to come up with the theory of an evolving universe. He had the right mix of talents of mathematics, physics, and phenomenology. The universe he came up with is well described by this sketch from an essay by Willem de Sitter in a prominent Dutch newspaper in about 1931. Imagine we live in 2 spatial dimensions, not 3. I must caution you, you should not ask the question, what is off the surface of the balloon on which you live? You aren't allowed to go there. Also, as the balloon is being expanded, you are not expanding and the galaxies are not expanding. Simply, the galaxies are moving apart from each other. Notice also that if you sit on one of those galaxies and look around you, you see the other galaxies moving away from you. You may say the universe is expanding and it's expanding around me, but of course every other observer will see the same thing. You will notice also that more distant galaxies are moving away from you more rapidly. According to a simple law, the recession velocity is directly proportional to the distance from the observer. And here, in the left, bottom left, you see Hubble's original evidence in 1929 that indeed this law is being obeyed. It's pretty messy, noisy data, but Hubble, with his colleague Milt Humason, by 1936, managed to get the left-hand side relation all the way up to a recession velocity of 10% of the velocity of light. Truly quite remarkable, immense speed of recession. I noticed that when they did this, I was 1 year old, and now as I reach the golden years, the relation has been extended by just 1 order of magnitude, as illustrated in the lower right-hand figure. We should look at some of the people responsible for this result. I'm pleased to recall that Percival Lowell, who was a scion of a prominent, rich Dutch family, after augmenting his income, decided that Mars might have an advanced civilization that is building vast canals. He used his money to build an observatory to look into this. His memory is honored by astronomers for his decision first to build the observatory in a site that is good for astronomy, not necessarily convenient to the astronomers, and second, for his decision to hire capable astronomers to instrument and use the telescope, and in particular Slipher, who discovered that the lights from galaxies are shifted toward the red, as if in a Doppler shift of galaxies moving away from us. To test out Lemaitre's ideas about an expanding universe, you need to be able to measure distances. Henrietta Leavitt showed us how to identify classes of stars whose brightness will tell you how far away the galaxy is. Lower left, you see second person from the left, the taller person, Edwin Hubble, who first proposed this linear relation between redshift and distance from the observations. Standing next to him on his right, Milt Humason. And then we see on the far right, a speaker later today, Saul Perlmutter. I was recalling with him earlier today that when I talked to him about this project of extending the recession velocity distance relation, he described it in early days, and I was thinking, but I don't believe I told him, oh Saul, this looks so difficult. But they did it, and made that extra factor of 10 extension with results that will be described that were really quite surprising. Another remark, one often reads that Edwin Hubble discovered the expansion of the universe. That's a bit of a stretch because Georges Lemaitre had proposed the theory and the observational test before Hubble. But one notices that as far as I know, Lemaitre was a retiring person. Hubble, on the other hand, loved associating with the rich and the famous and with with newspaper reporters. We notice Albert Einstein, third from the right. I bet that he is thinking now, I wish I were somewhere else. But Hubble put his name forward, and somehow that caused this reputation for discovering the expansion of the universe, perhaps. So what have we got next? Yes, well, we must skip a lot of history in establishing that the universe actually is expanding, but this is worthy of note. Here is an experiment in a hilltop near Princeton, New Jersey, at the Bell Telephone Laboratories, 1959, a precursor to communication by microwaves, a precursor, alas, to cell phones, which are not, to my mind, an entirely socially beneficial thing. But also, this instrument detected a sea of radiation. Here is the operative diagram. You see in this figure the engineer's careful accounting of all the radiation received by this telescope. You see circled in my red a temperature attributed to radiation leaking into the antenna from the ground. That was obviously a cheat, because that antenna, called a Horn reflector antenna, was designed to be very efficient at rejecting radiation coming in from the ground. That 2 degrees Kelvin actually is about 3.75, was this sea of radiation left over from the very early universe. Now, it's easy enough to say, I think this is a sea of radiation, but you have to know what is the evidence that this is a sea of radiation fossil from the early universe? The clue is a very fortunate circumstance. Because this radiation has an enormous heat capacity, it would be very difficult to cause its spectrum to deviate from the thermal spectrum it would have had in the very early universe. As Stephen reported, the expansion of the universe cooled this radiation, but it didn't disturb its thermal spectrum. In this slide, you see perhaps a very thin dotted line. That's a theoretical thermal spectrum. You see a colored line near the peak. That's not a theory, that's measurements of spectacular precision by 2 groups. You see lots of data points at longer wavelength. A spectacularly close match to a thermal spectrum. The universe, as we see it now, is optically thin at these radiations. Radiation at these wavelengths is not going to relax to statistical equilibrium. This is about as tangible a case for evolution of the universe as you can imagine. The universe had to have passed through a dense state where it was capable of forcing radiation to relax to thermal equilibrium. The universe has to have been evolving. I think this belongs in the iconography of great scientific advances simply for the deep result following from a very simple figure, although one by no means easy to have been made. So let's go on. This thing doesn't always want to go on. Oh, here we are. I return to this figure and will now explain the origin of the thing on the lower left. Einstein, as I said, took it for granted that the universe is static forever. His theory predicted that gravity will tend to cause the universe to collapse. He fixed that by introducing a term called the cosmological constant, logically allowed within his theory, but ad hoc for the purpose of giving the universe stability. Of course, that stability proves to be unstable. A slight disturbance, the universe will collapse or expand. It was Georges Lemaitre, beginning in 1925 and then completing in 1927, the interpretation of the astronomers' redshifts, Slipher's observations. The universe is expanding. The figure is the wording down below, and I guess I have to remind you, Einstein used a lowercase lambda for his cosmological constant. Nowadays, we use an uppercase lambda. I don't know why. On the lower left, you see that Professor Dr. Willems de Sitter's body has been replaced by a lambda, except the artist got it wrong. It's pointing backwards. The wording, what, however, causes the ball to expand? What causes it to expand or swell up? That is done by the lambda. Another answer cannot be given. That's somewhat ironic because we don't need a lambda to account for the expanding universe. We don't really have a solid, well-based theory for why the universe is expanding. We only have excellent evidence that it is expanding and evolving. But at the time, it was thought, because Lemaitre's first solution to the expanding universe problem was to start with Einstein's static universe and then follow it as a slightly disturbed universe would expand. So what do we got? Yes. Einstein, on learning of the notion of an expanding universe, wrote in a letter to a colleague, "Away with the lambda." To Einstein, the lambda was put in ad hoc. It's ugly. It spoils the logical simplicity of the theory. Away with it. Georges Lemaitre quite disagreed with that. He, in fact, saw the germs of the idea that the cosmological constant may be thought of as dark energy, now a very popular interpretation. Here is a copy of a letter that Lemaitre wrote to Einstein shortly after World War II, in which Lemaitre tried to point out to Einstein the useful aspects of a cosmological constant. Einstein's reply was polite, but it ended, "You may be right, but I don't think so." So, one last point. Other evidence that the universe is expanding, evolving, having to do with boundary conditions. We're all familiar with this phenomenon. Each of these pipes has a wave, sound wave produced, with a node at the driving point, at the point of instability at those slots, and an open loop at the top. Change the length of the pipe, you change the tone. The effect of boundary conditions. Boundary conditions apply also to our expanding universe. In the early universe, matter and radiation are coupled together by electron scattering. This produces, in effect, a fluid. The fluid has high pressure and not much viscosity. It oscillates. I think it's not worth going through all the details of how that oscillation produces a pattern of waves. Let's just take it as given that, yes, the universe, due to that oscillation, acoustic oscillations of plasma and radiation, produces a pattern of waves in space. Here is, in fact, observations showing the effect of these waves. On the lower plot, one has taken the distribution of galaxies on large scale, expand in Fourier series, which is to say plane waves, and squared to get an amplitude. The waves seen in that figure on the lower part are simply a statement of saying that there is a preferred length scale in the space distribution of galaxies set by the boundary conditions in the early universe. Now, the exciting thing is that those waves are present not only in the matter distribution, but remnant in the distribution of radiation. This thermal radiation left from the early universe is awfully close to smooth, as Stephen mentioned, apart in 10 to the 5th departures from uniformity. But these departures have a very definite pattern in them. The upper figure is a spherical harmonic expansion of the distribution of the radiation coming to the Earth. It's the analog on a surface of a sphere to plane waves in flat space. It shows the same pattern of waves. The wave patterns are somewhat more complicated, but actually very easy to compute because this is all done in linear perturbation theory. I think an undergraduate could grasp all of the elements of this computation. The same physical theory with its parameters, 6 parameters, is plotted, the prediction, in both bottom and upper curves. They agree wonderfully well. The bottom curve is measuring the distribution of galaxies fairly close to us, out to redshifts, we use that terminology, around 0.03 to about 3. The upper is looking at the radiation as it was released as free radiation when plasma and radiation decoupled as the plasma recombined. It's coming from far away. It's moved in a very different way through space-time, yet we see a wonderful consistency of these two results. This is the sort of thing that gives one confidence one's on the right track. Here, different measurements obtained in very different ways each subject to its own statistical errors, its own possibilities of systematic errors, and yet they're wonderfully consistent. I could go on on this theme for a long time. We have now developed, not I, but the experimentalists, a vast array of tests that look at the universe from many sides and produce a consistent story. Just a few remarks. On the lower right-hand part is a Hertzsprung-Russell diagram, which is to say a plot on the horizontal axis of the surface temperature of a star, on the vertical axis, the luminosity. This in a star cluster of great age. The one free parameter in this distribution is the mass of the star. The most massive stars are running up to the top of there. The least massive stars on the fat bottom are evolving still and burning hydrogen to helium. The shape of this pattern depends on the age of the stars. The age is great and difficult to understand if we don't have that cosmological constant. I could go on at length about all of these other measurements, light element abundances, polarization of the microwave background, dark matter around galaxies. It adds up to a consistent pattern that I think by now is so well cross-checked as to make the theory of the expanding universe as described by Einstein's general relativity theory about as compelling as it gets in natural science. Now, isn't there another? Well, yes, in fact. Let us pause to consider what an immense extrapolation we've made in this theory. Einstein's general relativity theory is well tested on scales of the solar system and smaller. But the scale of the solar system may be 10 to the 13 centimeters. The scale of the fluctuations we saw in those earlier plots, 10 to the 27 centimeters. Some 14 or 15 orders of magnitude. The theory has been extrapolated by a ridiculous amount, and yet the evidence is that the theory applied. An illustration, perhaps, of the conservative nature of physics. But it is also to be emphasized that we have no final theories in natural science. Each of them is an approximation, each is incomplete, and that's certainly true of this expanding universe theory. For example, the theory postulates dark matter that is more abundant than baryonic matter. What's the nature of this dark matter? We don't know. One may say that it is purely hypothetical, except that its presence is convincingly established by the broad variety of tests that the theory meets. The Einstein cosmological constant has a value that is, in a sense, absurd. In terms of fundamental quantities, it's an energy of about a milli-electron volt. It's insulting, and yet there it is. And what in the world is the meaning of this parameter? Then there is the question, what was the universe doing before it was expanding? Stephen Hawking has given us a very attractive answer, but to be blunt, I don't think that the evidence for that theory, inflation, the no boundary condition, is anywhere near the evidence that the universe has expanded from a dense hot state to its present situation in a way described by Einstein's general relativity theory. So I'll just close by making a general remark. Well, of course, I love this quote from a noted authority on philosophy and baseball. You can see a lot by just learning, by just looking. Yeah. Here is a sample of the people who have done the looking with great, enormous care, ranging over now a century. Interesting to recall that in 1916, Einstein produced his first theory of the universe, which he soon dropped. 100 years later, we now have a theory that through the work of these and a significant but not enormous number of other people, fits a vast amount of evidence. It's by no means the final theory of the universe, but we can be pretty confident, I think, that it's a good approximation. Thank you.